Alright, so here we have a bucket of mass 8 kilograms. It's filled with water and it's attached to a string of length 0.5 meters. Part A asks us what is the minimum speed of the bucket that it has to have at the very top so that the water does not spill. And then part B says if it continues with the speed, what is the magnitude of the tension in the string at the lowest point of the path. So here's the bucket of water, here's the top, here's the bottom. So let's go ahead and crack this out, okay? All right. To do part A, I do want to point out that it says at the very, very top, and then it says minimum speed. So these conditions are important as you practice. All right. So I'm going to go ahead and draw them from my free body diagram for the bucket at the very top. Not drawing a scale here. At the very top, f of g here is pointing down, and then there's also a typical tension in the string that is also pointing down. Okay, so that's what you would typically set up at the very, very top. You have two forces, T and F of G. Okay, and then from there you can set up your centripetal force. Your centripetal force are both of these vectors added together, typically. Okay, however, part A asks you what is the minimum speed that the bucket can make it all the way across without the water spilling out. So this is important terminology. In this case, minimum would imply that the tension in the string is going to start sagging, right? It's at that critical value, okay? Therefore, the assumption is that T is going to go to 0 because you're trying to find the minimum speed, not maximum speed. There's no, I guess for this one at the very top, there's no such thing as maximum speed. You can only find minimum speed because anything else greater than that will work. So anytime you see these or this terminology where it says minimum speed at the very top, you are expected to cancel out T because that's where T will start to sag, and therefore I'm going to go ahead and eliminate T from my function. Well, if I eliminate T from my function, I'm also going to visually erase T from my free body diagram. So at the very top, anytime it says minimum speed, the only vector that you should draw out is f of g, right? I started with what you would typically draw out, but then hopefully as you practice, terminology tells you, wait, erase certain vector. In this case, between t and f of g, you cannot erase f of g because f of g always exists. Therefore, t will disappear at the very top when it says minimum speed. So now really your f of c is just f of g because f of g is the only vector pointing towards the center of this circular path. And if you were to break up f of c down to mv squared divided by r, also break down f of g, which is equal to mass times gravity. So you notice your mass will cancel out, okay? And then to get v by itself, or v squared by itself, I will multiply both sides by r, or I just move the r to the top right. So v squared is equal to g times r. Well, this is v squared. So to get v by itself, we need to radical both sides. So radical both sides will leave you with just v on the left side, and then the square root of gr is your minimum speed function. So keep this in mind as you practice. Anytime it asks for minimum speed, this is it right here. Vmin is equal to the square root of gr, okay, whatever r is. So I'm going to plug in g as 9.8 meters per second square. So you notice here this is a positive 9.8 because the, well, one it asks for minimum speed, so there's no need to plug in a negative sign. Okay, because if you plug in a negative sign, you can't take the square root of a negative number. So you're just trying to find speed. Here's 9.8. The radius given is in the statement as 0.5. That's what I'm just going to plug in. And then 9.8 times 0.5 is just 4.9. And if you do it correctly, square root of 4.9 will give you a speed of about 2.21 meters per second. All right, so this is the minimum speed that the bucket has to be moving at in order to make it all the way across so that the water doesn't fall out. So that is our answer for part A. Now let's do part B. Okay. Part B says the lowest point, right? It says if it continues with this speed, assuming that it continues with this speed. All right, at the lowest point. So let's go ahead and set up the physics for part B. Okay. At the very bottom, the bucket, there's an f of g, again, pointing down the page. There's a t pointing up. Here, I purposely drew tension a little longer because it is in motion. The tension has to be pulling, quote unquote, the bucket upward so it continues to move upward. I kept the f of g vector about the same size here. Okay, so at the bottom, it's important that you draw t just a little bigger in this case because I don't know how, well, I know how fast it's moving, but mathematically I don't know what the ratio is between t and f of g yet. All right, but the point is that draw t a little bigger. It cannot be the same. In case you're asked to pick a free body diagram, you do not want to pick one that have two equal magnitudes. because that's not the case here because it's constantly moving, being rotated in the vertical plane. All right, so let's go ahead and set up our net force. At the very bottom here, my starting point is slightly different just to help you see these things. Net force equal to centripetal force, and then, well, I know my net force is just mass times acceleration, which is m. What's the a? A centripetal, and then F of c. In this case, you have t pointing up along the y-axis. You have F of g pointing down along the y-axis. Both these vectors are along the y-axis. So we will subtract t is pointing upward, F of g is pointing downward against it. So here I have t minus F of g. Once again, the negative sign here is already taken care of for you in terms of the F of g vector. Well, we're asked to find t. So I want to break AC into v squared over r. Okay, and then the right side hasn't changed. And then I want to move the F of g because we're asked to solve for t. So this negative F of g will be moved to the left side of the equal sign. So now we have FC, which is mv squared over r, plus F of g, which is equal to t. And then really here we know everything already. We know m is 8 kilograms. We know v, it says b if it continues with this speed. So whatever I found in part A, I'm just going to use it because it sets to assume so. So 2.21, square it, and then I'm going to divide by r, which is 0.05 meters. And then F of g is mass times gravity. Here's mass, which is 8 kilogram. Here is gravity. But again, I put in a positive 9.8 here because the negative sign was already taken care of for you in the second line of my work here at the very top where I'm circling with my cursor. So here, don't plug in a negative, plug in a positive, okay? And then if you plug those in the calculator, you should get 78.15. Oh, this should be a plus sign, excuse me. This should be a plus sign. I'm sorry for that. That should be a plus sign. I don't know why I put a minus sign. Okay. So anyways, if you add those two vectors together, or the sum of those values, you should get a tension of, okay, about 156.55 newtons. Okay. All right. Other than that, that is the answer to part B. And it says magnitude. So I'm just going to leave it at that. If it didn't ask for magnitude, you would just say, towards the center of the vertical plane. All right. Or upward along the y-axis at this location. Okay. Stay nerdy. Don't be back.